Thank you very much, and it's a real pleasure. It has been a wonderful meeting for me. Because of my current work, I typically have to go to many meetings, but this one is awesome, to the point that I want to be in all the parallel sessions, and it's hard to choose. So it has been really great. So let me tell you a little bit about the DARPA work on lifelong learning machines. So in the human level AI and in the general AI, we have very high bar to reach. And in DARPA, we wanted to have a very particular bar because we run projects, and we want to have a project that is something that is new, that is not there yet, but that we believe can actually happen in a number of years. And this is a particular subset, perhaps, of AGI, and what I would consider a very important step forward, but I think that it's doable. I know it's very funny to have your picture on the thing, but this is the current DARPA style. So it's not my artistic choice. Okay, so I don't have to talk about much AI today, but it is very impressive. And we should never forget, once we talk about that we want to have more general AI and better things, that it is impressive. And in many applications, when you compare what you had previously, where you had to write a program and to make a rule-based and ask experts how they solve problem, and now instead of that, you take training set and a training algorithm and a neural net, and let the neural net find it. Even if you don't understand what it does, it's still doing usually amazing level of classification. So this is all really great. At the same time, the limitations are there that sometimes they're really dangerous. And I think this is one of the things that makes governments worry, that if we trust everything that companies tell us, and they sometimes tell us that they're already there, they already solve all the important problems, it can be pretty scary when it's not exactly the situation. So the issues in today is that AI systems compute exactly what they've been programmed for or trained for. So it works very well for games. It works very well to recognize images similar to the ones you saw. But if it has actually to work in the real life, in the real world, things can happen there that you were not trained for. And then what would happen? So it's true, many neural networks that are well done will have quiescence region where they will do nothing if they don't know what to do. But this is by itself can be dangerous. If you do nothing in situation like that, can bring to crashes. So the question is, what's the problem and what's the minimum thing that we can bring to AI in order to make it reliable again? Something that you will want to have in your car or in your home, or something that you can feel more comfortable. So the way to look at it is that there is no way to prepare for any eventuality. So we are going to be there in things that we didn't learn about. So the question is there an easy fix? Is there a way that I think kind of makes sense? Let's say you had a self-driving car and it learned on billion examples, and now it had an accident. So it makes a lot of sense to take the last 100 frames from recent occurrence and play it back and tell the network, just learn this 100 already on the top of the neural network that holds billion of examples of knowledge. So this will be very good. So let's say you had billion, you had your network study, and now you have the new 100 examples. You take the new 100 examples, now you know the answer because the accident already happened, and you know what's happened, you analyze it. So now you have input and output, and you put it in your neural network by training it. So how do we train neural network? We do one of the training algorithm, and we write over all the parameters, or what we call weights in neural networks. So we write over all the weights, and now the network is really good in the sense that it really knows what to do with these 100 recent frames. Now, what's happened with the previous billion examples? Their information about them was held in the parameters. But we took the 100 recent one and retrained these parameters to have the last 100. So the previous billion, maybe some of it is there, maybe none of it is there, maybe most of it is there, we don't know. It depends how the 100 and the billion are related to each other. And in general, that's what we call catastrophic forgetting. And that's the issue, the main issue in current AI, in current neural network in particular, that if you have one training set and you learned it, and then you have a second training set and you learn the same network, you're likely to forget many parts, important parts of the first training set. So if you do that, then it's very, very different than the way we learn as people, because you went to first grade and then you went to second grade and you learned more things, but it doesn't mean that you have to forget how to read and write because you don't relearn it in the second grade. And then you go to the third grade and you better don't forget the basic algebra that you had in second grade. So you don't have all the time to reinforce and remember, repeat all the time. You have this thing that what you learned, and it has to be there. If it's not crucial for your life, you may forget it, kind of like calculus too. But other things that are kind of basic, you retain. And this is what we don't have in current AI. And this is like something that you can put your finger on. And so I would like to have these kind of networks that I can add more and more training sets on the go and not forget the previous one. We just have to be very conscious of that and think how we can perhaps solve it. I want to add the third point that it's another point that kind of worry large boards of people when you have companies that tell you don't worry that there are little errors here and there, because when everything will be automated, when there will be Internet of Things and all the cars will be automated, then everything will be fine because the computers understand the computers and everything will be good. So this is one option to look at the future. Another option to look at the future is each of them will contribute its own failures, and together there will be a big party of huge failures. So we want to be ready, and we want to get to the point where things can learn on the go, at least have the second training set after the first, and continue and continue. So we know that in nature this is the basic of everything, and if we see that in nature it's the basic of everything, it means that there is a solution, and the solution is perhaps something in mechanism that evolved over years, but we are smart and we have all kind of evolutionary mechanisms also in our life as scientists. So we should be able to do something like that and to understand that intelligence is really not only about calculating fast summation or playing chess, it's about adapting to where we are. That's what we want to be. You don't want to have the same discussion with the same person over and over again or repeat your first grade behavior. So what I want to bring here is just to bring two very general notions of biology as a way that perhaps we can use them too. So for the last 10 or 12 years, I worked more in neuroscience than I worked in computer science. And my area actually was memory reconsolidation. So I'll tell you what it is and why it's so crucial for us. So when you remember something, when you learn something new, you consolidate it into your memory. Then it's there. Now, once you have to use this, so the information in your brain is not organized like on a tape, like in a very fixed type of memory, but it's somewhere in your cortex, and now you have to bring it in order to use it. Once you bring it in order to use it, or recall it, and it can be conscious or not, it doesn't really matter. What happens is that you have a window to put back this memory. So actually, when you take the memory out and you use it, it's not exactly where it was before. And you have to put it back. When you put it back, you use some enzymes and some chemicals similar to what you did originally in the consolidation, but it's called reconsolidation. There is a little bit difference because it was already there, it already had associations, and you need to put it back. So you have a similar process to consolidation. It's faster, it has a particular windows, and there are many, many papers that will show you that if you did something to stop the reconsolidation, and these are usually by bad means, like stop particular chemistry, then this memory will no longer be fully there. No, it's not only a negative thing, it's actually a very positive thing. So while reconsolidation was treated in as it is for the last 15 years or so in research, I think that psychiatrists and psychologists knew about it for many years because they got people that had traumas and talked to them, and then these memories went up and these memories went back, But as they went back, as we all know as engineers, they never come back the same way that they were treated first. Now it's different. Now you remember the memories that you had before, but they're associated more smoothly. Maybe they're associated with a cup of tea, or with a soft voice, or maybe with these beds that you see the Freudian psychologists talking to people. So you can actually change and make things better by bringing them over and over again. So why do I bring memory consolidation? Memory consolidation is the way of adapting our memories, or who we are, or what we know. So if you got married in your 25 and you remember your spouse to be very young and handsome, and you reach the age of 50, your spouse does not look the same, but you remember him from the way that he is now. So actually, reconsolidation allows you to live the moment. So you are now as it is, and you remember some pictures, or maybe wedding picture, but it doesn't matter. You live the way it's now, and it's not a dangerous thing when we were not there in order to remember everything well, but it helps us to be in the moment. Epigenetic is another great way that helps us to be in the moment. So there are still genes, there is still genetic, but there's a secondary way to adapt and change it to the next generation by what's happening now. The reason I bring this to is to say, you know, in addition to evolution, there are so many ways that biology allows us to be stable and at the same time to adapt. So there is kind of, it's not that you forgot everything. If you change and improve and live the moment and live the current future, but safely. So why wouldn't we do it in computer science? So why wouldn't we do AI exactly like that? There is really no reason. So what we do in current AI is we very much attach to the particular 9036 model. And this is a great model. There is no reason not to be attached to it for many years, but perhaps we attach to it a little bit for too many years. So the notion of the whole Turing model is that you have a universal part in between, which will be kind of our mainframe. And this mainframe does nothing. It just sits there, and it will do nothing until you load the program on. And once you load the program on it, it will do exactly what the program wanted. So it's a great idea, and it allowed to the whole field of computer science to be the way it is now. And in terms of AI, it allows us two types of AI. One AI that you write the programs really writing it, the programs and the rule-based, and the other type of AI that we mentioned, which is the machine learning, that you have training data, you have fixed training paradigm, and it's still in the Turing way, in the way that the machine learning is here. So you actually train your network. So it's perhaps one step towards doing something else, but you still freeze it before you put it into the mainframe. So this is the current neural network. You have the training set, you train your network, and then you freeze it, and then you start operating. So in that way, it goes with the Turing paradigm, while it also saves you to the work of a working and understanding. Now, Turing was real genius. There is a reason that we take every word that he said very seriously. And he told us already many years ago that the development of the what you call the Turing machine, or the general calculator, is to have this system that work in a disciplined but unintelligent manner. But for many years after he finished his work on the machine, and after he finished his work on breaking the code, he worked on his wish to simulate human brain. It was his notion of having AI that learned from experience. So he was talking about it, and as I say, one good person to follow. So what can we do in computer science? So from the theoretical part, we know that actually we have a way to talk about machineries which are not exactly in the Turing paradigm. And in fact, there is a whole continuum that's starting at the Turing paradigm and reach all the way what we call super Turing or modifiable programs. So there is a whole way that you can modify your program smarter and smarter, or better and better. So there is a whole hierarchy. If you can just a little bit change, then you go one step above Turing. If you can modify more, you go more. And this actually, you get some particular properties from this kind of thinking. One of the properties that you'll get is that when you think about saving energy or saving resources, in the super Turing paradigm, you use only as much energy, as much resources as you require. While in classical computer, you will do all the things the same. So I just want to give you 3 slides to explain about it a little bit. So in general, when you think about neural network or analog recurrent neural network, you think about a dynamical system where the weights are sitting around and there's these neurons around, and you don't have the separate program that's working on digits and putting things in memory on the side to read it later on. But everything is combined. So the real question is, what is there? And what we showed many years ago, that you can have Turing machine capabilities, but in fact you can have something more. And I'll tell you just shortly to explain what it means by having something more, because sometimes it's weird when you hear it the first time. So if you want to think about neural networks, we can think of very simple neurons that will just have linear or affine combination, and you apply some nonlinearity on the top of the neurons. It's not really matter so much what type of nonlinearity you have. There are very little requirements. But interestingly, if that's the only description that we have about a neural network, to have some number of neurons connected and calculating this at the same time, we can see that what we get is actually a versatile model of computation. It depends on the type of properties that we add to these neural networks or that we put to the neural networks to get all kinds of computational capabilities. For example, if we'll have the weights to be very simple and the network will be deterministic and synchronous and predefined, so the weights will not change, or if we want to have values which are defined on fractals or in rational numbers, in that case, we'll stay in the Turing paradigm. If we go ahead and change the calculation either by talking about real numbers or by having a biased coin, so rational numbers before by having a coin that can help us in the computation or have asynchronicity, or allow for evolving and modifiability, we can get all the way to the super Turing paradigm. And in between, if we have everything in between rational or real weights, if we have something between deterministic and stochastic, if we have things between synchronous and asynchronous, all these hierarchies, we give this continuum that will give us this continuum hierarchy of the super Turing. So just kind of to paraphrase what we have. If we have things very simple in neural networks, we have just neural Turing machines. And the neural Turing machines can have whichever activation function. So in the 90s, we already have this sigmoid activation function if you want to have differentiability and to learn in backpropagation. If you want to take it seriously, people also did, my group and other groups worked about neural compilers, where you write in some language, high computer-right languages, and translate it to you to a neural network. So then you have a basic neural network so that you know exactly what it does in each part. And once you learn it, you also know where things came from. So you have much better explainability, which is another way. So if you kind of take in face value the neural Turing capability, then you can have all kind of very interesting capabilities. And I wanted here to give credit also to Google DeepMind, which shows how you can not only run compilers and not only have copies and parentheses check, but actually how to learn on the go these functions. So now there is more capabilities. And then in the more general paradigm, or the full super Turing power, it's the way that we can think about it is assume that for every input to your Turing machine, you have also an advice. And this advice is bounded by size, so it's not long enough to give you all the possible answer. And it has this feature that for all inputs and the same length, the advice is of the same length. So it gives you something more than Turing, but not everything else. In other way, you can think about having very smart pre-processing, and after the pre-processing is done, you can compute efficiently. And this is the way we think about super Turing. We don't need precise infinite weights anymore. We can do things in a modifiable way and in a learning way and have the same exact capabilities. So in the way that we want to think about super Turing of lifelong learning, it's really our way to building physics that is now in the computer. So we can have growing precision that is similar to zooming or to attention. It's very similar to what people talk in cognitive psychology. They're talking about the cognitive miser. The cognitive miser is actually my son, who just finished high school, and he knows exactly how to learn the minimal and to play the most computer games and still finish with A. So this is the example of the cognitive miser. And another way to think about it is minimizing energy, minimizing free energy, minimizing other energy. Another way to think about it is that you compute, but once in a while you need more, and then you need to learn the next input. And the last way that I think about it is a physics. In physics, we're talking about chaotic systems that diverge exponentially away from initial points. These networks also diverge exponentially based on their initial condition, but we translate it in the opposite way. Instead of saying they run away exponentially, we say we care only about the first linear many bits because they will tell us where we'll be at the end. And if we stop after some time, then we don't need to know more than something. So it's kind of recreating chaotic systems. And in fact, you can show that you cannot simulate chaotic systems well enough on regular digital computer, but you can simulate them very well on neural computers. And the other way that I mentioned here, you can have a very simple neural network and just have a coin. And if this coin is exactly equal half and half, you'll have this class that is called BPP, which is the largest practical class of problems in theory. But if you have a coin that you don't know what this information is and you still use it, you can get extra power, and that's very interesting. So we'll summarize it in this way. If we go to lifelong learning, we have already a theory that can help us to build it, that will take us all the way from Turing machines, where when you change input, the output changes, to super Turing machine, that when you change the input, the program changes. And you can reach to this in so many ways. You can move from discrete value to analog. You can go from deterministic to randomness. You can go from pre-programmed to lifelong learning and evolving. And you can go from one algorithm to a series of machines. And why do I say the last one, which is so important? So in nature, all of us all the time follow one algorithm for everything. So if I want to shake your hand, for example, so we just shake hands and you didn't have to think about how to do that. You just gave your hand back and did it nicely. And you didn't crush me and you were not too soft. So we don't want all the time to think about things. With Turing, we do all the time things immediately. On the other hand, if I come and I want to shake legs, this is something we're not used to do, then you have to think what to do and maybe to adapt something for the next time, and that's where the adaptation goes. So while in any point of time we have one algorithm for thing, we have our Turing machines there, the whole process will be super Turing. So the Turing and super Turing are not against each other. They together describe nature. The capability to follow now and the capability to work in the background and adapt. And that's what we want also in lifelong learning. And I just want to give a credit. I love to give credit to people. So I want to give a credit back to Turing. While I was thinking just, how can I get a computer that will be stronger than regular computer, Turing was far ahead. He was thinking in his time how we can have new AI. He was talking about this new AI and coming with exactly these 4 properties which can give him this AI like the brain. And there is last one point that I want to say about it. So if we're talking about machines that never stop working, so we're not anymore in the frame that you give me question and I'll give you answer, but I want this paradigm, let's say a security system. I don't want it to stop after one person that comes into the room. I want it to continue working. Or if we have all kinds of other systems that we want them to work all the time. There is unbounded input, unbounded output. In general, we have a very large space of sequences of bits, 2 sequences of bits, which is 2 to the 2 to the Aleph 0. Aleph 0 is the smallest infinite cardinal that correspond to natural. If we have only Turing machine instead of this brain, we'll have Aleph 0. If we'll have neural network, real learning neural network, we'll have 2 to the Aleph 0. What does it mean? It means that if we change to lifelong learning, this is no joke. We're not anymore in the same paradigm of current AI. If we're not training in advance and stopping and freezing, but if we can change, we can actually go to more input-output functions exponentially more. This is like a totally new paradigm for AI. And that's why, that's kind of what's standing behind the lifelong learning. And perhaps as half a joke, you all know the Turing test. So the Turing test, the judge has to separate between the Aleph 0 many answers and a human. So perhaps the super Turing test will be to separate between 2 to the Aleph 0 and human. So, you know, you can hypothesize it will be much harder. Okay, so for example, if you wanted to think about the brain as an example for super Turing computer, but it's just one example. You'll have some plastic nodal network that will have some parts which are hardwired, like pains and pleasure, like hormones, like some goals and some limits, but many other things that you can adapt over time. So why do we care about lifelong learning so much when we come to practical systems? So in general, many of us say, well, you know, Facebook and Google, they really have so many inputs. They can learn forever. It doesn't matter if we stop them or not. And, you know, if they want to play Go, they can take the AlphaGo to the side for another year and a half and to retrain the system and then to win again. So that's good, and that works for some companies, perhaps. These 2 companies and others. But if you have a robot, if you have another system that you wanted to learn from the data that you have, and you don't have millions of data, but you want to start working with that already, because you want to give your mom, your elderly mom, a good little robot that will be able to start working now. So you train with whatever you train, and then by the time that it's fielded, it collects what it does and it becomes better and better. So this is the left way of thinking about it. The right way of thinking about it is you want to make it a safer system. You don't want it to collapse just because you are not ready for something new. So if this something new is not stopping, it's not like something that happened once, but there is a change. There is a robot that has to take care of your mom, and your mom fell down, and there is a real change in behavior. You want the network to notice and open up and retrain itself and do something right. So there are a few capabilities that we would like to have in lifelong learning. So as I mentioned at the beginning, lifelong learning is much more humble than general AI. Okay, but it has a very clear definition. It has a very clear computational capability, space capabilities, and perhaps a roadmap to achieve it. So we have a few features that we would like to have in lifelong learning, and that's what we ask is part of the definition. So the first one, we would like to have what we call this continual learning. And going back to the beginning of the talk, continual learning is this capability to have a second training set after the first training set. So you don't have to stop and you wouldn't forget. The second capability is adaptation to new tasks. And I'll tell you what it is. So in many systems, you can have a large database and you'll take the memories, the thing that you see now, and put it in memory. And you'll take the things that you see in 2nd grade and put in memory. And you take the things that you do in 8th grade and put in memory. But then you need to do something with them. And you have all kinds of memories organized by some way. And the real question is, can you work very fast to new tasks by considering all this knowledge together? So I think that when you have memories, you don't organize it by time, you organize it by some other ways, and that's why you're able to solve things fast. So that's what we want. We don't want just to add gradually more to the memory. We want to have a functionable one. So that's kind of just to say in 2 that we want it to be functionable, not just to be able to get this memory somehow, but actually to use it. The third one is another point that is very interesting. And if you work with psychologists, it's become even more fun. So think about AI or current neural networks. They always have this training set. And we talk a lot in neural network of whether the training set is labeled, that they tell us the classes, or maybe it's unlabeled and we need to do clustering algorithms. Maybe it's semi-labeled and we can do some clustering and then give it some labels. And maybe it just gives you grades and you do reinforcement. We are in a totally different paradigm. In lifelong learning, think about yourself. You go into a meeting. Who gave you the training set? What is your training set? So you decide your training set. You decide what you take from the outside to just strengthen your belief that you had before and makes you feel good. So maybe you'll take in kind of like to strengthen, to better understand, to better zoom in some ideas that you have. Sometimes you see something really weird and you decide not to keep it because it's stupid. Sometimes you keep it as a joke. Sometimes you keep it and think about it later and say, that's actually an interesting idea. Let me follow. But you decide what's your training set, and you do it in a goal-driven way. All animals do everything in a goal-driven way. So I'll tell you what a goal-driven way is. Let's say there is here a stale Cheerios. So if you were in a NIPS conference where they don't give you any food, so you're a student and you don't have enough money to buy food, and you see the stale Cheerios there, you kind of put it in your pocket, and after the talk you swallow it outside. But if you're in Prague and you don't stop eating because they have all this amazing food all the time outside, you'll just clean the table from dirt. Okay, this is goal-driven perception. So your perception is different based on where you are and what you want to have. So that's kind of an answer of what we want to have in lifelong learning. It doesn't mean that you cannot ask humans for answers. It doesn't mean that you cannot be active. It doesn't mean that you throw human from the loop, but it means that the machine has some kind of say of what it wants to take in and on. The last two will kind of go fast, is the selective plasticity. This is a general issue of machine learning. Here it's become a little bit deeper or harder. We want to have the system that is not changing all the time, because this is a mirror, and you don't want to have a system which is a mirror. On the other hand, you don't want to have a stiff system that doesn't never change. So what's the thing that you want to do is the thing that you'll create in your lifelong learning application. The last is safety and monitoring. We all kind of worry in some way of what AI can do once it learns. These systems can learn on the go. How can we make sure that they learn within the paradigm, within the framework that we want them to learn? So if this is a system that has to give me advice about restaurants, I want it to continue giving me advice about restaurants instead of start shooting random people on the street. Okay, so there are some things that make sense. There's something that you want the system to run forward, because if you think about us, we can change a lot in our brain. We can change a lot of connectivity, and still we kind of do the same thing. Even if our body can do others, many of us don't jump from the roof. Many of us do not strangle random cats on the street. This is horrible thoughts. Why did I even say it? I have wonderful cats that I love. But I just kind of try to go like really gross, extreme. So why don't we do that? Some of us because of morality, some of us because we run prediction and we run simulation. And I say, well, if I jump from the roof, it may be really fun on the way, but then it may not be fun any longer. Maybe my children will not be very happy. So you kind of go forward and think before you do something. Most of us are like that. It will be smart of an AI system to do that too. So the way we run the lifelong learning program, we run it by having two technical areas. One technical area are the computer scientists. They have to give us a system that slowly we help them over the 4 years to build a system that will have all these capabilities. They will not do it immediately, and currently we're already half a year in, and we already are tackling pretty interestingly the continual learning part, which is the first. But then we have the TA2. TA2 are biologists, and they're not necessarily neuroscientists. So among our biologists, we have all kinds of people. We have a person that is actually Allen Institute of Boston that are playing with Planera. Planera is this worm kind of that you cut it and then it regrow its head and tail. So you cut it when you get 2 of them. But if you put electrical field, you can get this Planera with 2 heads. If you cut it differently, you can get 4 heads. It's kind of weird. But once you cut it again, it keeps its last morphology. So there is some changing. So what we kind of realized that in biology, there are lots of lifelong learning, not only in brains. And it's interesting to look at humans, but there are things that we can look at lower animals and already get some interesting ideas. So we can get from human brain, we can get from mammals, we can get from smaller animals. And the question for the biologists is not go and copy to us brain or go and copy to us the Planera. No. We ask them a particular question. I want to know how your system continually learn without forgetting. I want to know how your system organizes this thing so it can actually use it and create what is needed to be created. So these are the questions. We don't let them to play everything. We have particular questions. So I want to give you just some examples of what people provided so far, which is kind of cool. So I just chose 6 examples, and I'll talk just a little bit of what people started with. So this is a company. And this company is talking about going after the work of Papert and Piaget, and they're talking about grounding a language. So there is a robot, and this robot is playing, and as this robot is playing, it also learns the symbols for that. And what they create with multimodality and with trying, they create some understanding of words with the application for personal assistant technology. That's their direction for lifelong learning. There is another group from Columbia that what they do is they build networks that generate themselves. And what they want to reach by the end of the year is neural networks that generate better neural networks. So they want every neural network to be better than the previous one in the way of continually learn. Their application is very interesting, is in a particular way of thinking about a robot. So what they want to have is this robot that understands how it's built, and then separately it will understand what it needs to do. So once you take it out from the computer, you will not need to wait a long time for it to refine what's in the real world. It knows something about itself, it knows something about the world, and usually you have to change one of the 2. So if a leg is broken, it will change the understanding about the self and will just kind of fix it faster. Another way is a group from MIT and UMass. And what they do is they talk about agents that play surrogate tasks. So what is surrogate task? It's something that we do all the time. We don't think about it, but it's a really nice idea. So think that we have just a vision picture here. So we can kind of hide this picture, a piece of the picture from us, and ask, what's there? So like here, this is a surrogate task that we hide something. Another surrogate task can be, we have a picture, we know what's here, and we're asking where this one should be relatively to that. Or if we have a movie, a video, we can cut it into frames and try to put it in different orders, and then ask which are good orders and which are bad orders. And once we do these different orders, we start learning something. We start learning something about how balls should fall. We start learning here something about relationship, about some semantic, if we take the color off and put the color back on. So why do we do this? So the notion is that in real life, we don't have a lot of labeled data. So what we do, we take the data that we have and make it into a labeled data. For example, if I want to remember now that it's red color, I can say, okay, this was a red color. Let me look at the room. Everything will be gray, and I will paint it, and I will paint it red. So now I remember what it was, the red color for the chairs. So this is a way to remember relationship. They use it for what is called intelligent search. Intelligent search is like, for example, a robot that is going here and looking for a particular thing. It can see only a little bit what's in the rooms, and it's supposed to go to the right place, even if it is a little bit, because it already knows that the banana should usually be in the same room with the refrigerator, even if it's so very little of that. There is another group from Wyoming. The person actually is now in Uber, so we have a little bit working with Wyoming and Uber together. And this is a notion of using something that is similar to neuromodulations, which are context-based, where especially there you see like there are kind of special areas that are organically coming together based on things that happen. So why is it important to have this kind of regional parts? Because then when we want to relearn or to update, we don't have to relearn or update the whole network. It will actually tell us which part of the network you can update now, instead of, and it's something that will fit and will not ruin other things. So just to mention, there are many methods that people are using to decide which part of the network to learn, kind of looking what was not used before. But this one actually can grow. So you can go with this to many, many tasks. So there is like no comparison to things that were before. I want to mention also this group that work on index code, which are code that explain how the hippocampus put memories into cortex and take it back. This is a group from California. And the last one that I mentioned already before, this is a kind of interesting experiment. They put a new eye to this animal, and they can see that the animal have more capabilities and it can actually walk backward, actually start using the new eye. So there are these capabilities for low-level animals. They're using it for flexible robotics. So let me just run here. Oops, I ran too far. Yeah. So we just want in lifelong learning to have this capability to have a system that become better and better. There are many questions that come when you talk about lifelong learning. So while it's still a very small part of general AI, perhaps, there are still questions that come. One is when we look at regular neural network, we usually know that we spend a lot of energy for the learning part, and once it's fixed, it's cheap. If this network never stops learning, does it mean that we'll always spend a lot of energy? So it's not the type of things that we are able to do. So this is one question. How can we keep safety? How can we measure success? So currently, when we're talking about classifiers, the way we measure success is by looking at a test set that is similar to the training set, and we see how it transfers from the training to the test. If we want it to transfer to something else, how far should we go? How should we test it? There is a big question of how can we keep ourselves, the researchers, from falling to the programming tricks that we know. How can we not, at the end of the year when we have to make a presentation, just put there something that will say hello world, so that the system does something at the end of the word? And how can we keep a human in the loop, but in a way that empower the human instead of bothering? So in lifelong learning, we have a construct that we made. We call it the center group, and the center group is where we're going to try to have young people that we encourage them together to become the new leadership for the lifelong learning, and we do it in various ways. We have meetings, we talk about different parts, we read together papers, we solve together problems of one group by the help of other groups, and we actually become a community by doing that. We also invite people from the outside to do that. So we have a large amount of groups. It's a very large program. But we're still open for people from the outside that feel that they can contribute to the center group, or that there will be natural reason for them to join us. We're still open for that. And just to mention, the performers that we have are actually from many countries. So there was nothing that said that people cannot come from outside the United States. And we have actually people also from a few countries in Europe. And with that, I just want to thank you very much. And I'll finish my talk.
Okay, first and foremost, thank you very, very much, Hava. Then we have a bunch of questions for you. Starting with one by Jeff Thompson. Jeff, where are you? Okay, and Jeff wants to know, DARPA has projects for lifelong learning and explainable AI. How are their goals related?
Yeah, so DARPA has a few projects in AI and continue to put a lot of effort in AI. The projects are running independently. The program managers usually are friends. The one who runs the XAI is my best friend in DARPA. So the connection is kind of behind the scenes.
Joseph Davidson. Okay. Can you give a specific example of a function which the super Turing models can compute as opposed to a model specified to support self-modification, for example, random access stored program machines?
Yes. So there is a difference between theoretically and practically. So theoretically, you can show that the super Turing model will solve the halting problem. So this is a theoretical construct, and you can show it. In terms of the lifelong learning, we don't have it yet. So at that stage, we have a few measurements. So we created a few experiments that we want people to do. And they include environments that change over time. And they include data analytics that come from multiple sensors that change their distribution over time. And these are the things that we'll do the first. In the second, you will start working on farm maintenance. So if you have a robot somewhere far, or you have something that you want it to still work a little bit before the next thing comes to work it out, you want it to have self-maintenance to still do things. So we kind of like a good AI thing. We think about positive things.
Then, direct follow-up by Jan Shinkora.
Up there.
Oh, balcony. First timer today. How much does a program have to change itself for it to be considered super Turing? Surely changing a Boolean constant back and forth is not enough.
It's enough to do the most minimal. So if you had, so let me answer to you like theoretically, if you had a system that had only binary weights, and the binary weights would change back and forth, this is already super Turing. So the way that it will change will have to be smart, but the amount of things that it change can be very basic. Just the minimal change, and you're in another world. And the reason is that you do that, just this minimalistic change, and maybe later another minimalistic change. I think many of us work like this. I think actually animals work in minimalistic changes, except for in movies, where in one day you understand that all your life were wrong and you become a new person. But I think that most of us make little changes.
Jan Sweeney, over there. Could you explain a bit further about the diffusible plasticity idea? Is it that weight updates are shared across neighboring neurons, or is it something different?
That's very interesting. So the diffusible, the way that the Wyoming group are doing, they're building it in a spatial construction. So they actually, I think, took after the notion of neuromodulation in brain, and then it creates regions that become related. In reality, you have also areas that can be affected by the same neuromodulation. I want to say one more word why they do that. So in reality, if you think about it, our neurons are very plastic, and the way that they work differently under different environment and the different neuromodulation. For example, when you're tired, you feel that you work differently. If you took one of these bad substances ever that you shouldn't share with us, you may also feel that you're in a different world. So under different situation, you work differently, and that's what happened under these different neuromodulations. So actually changing something about the activity of the neurons. They build it specially. I don't see a theoretical reason to do it not locally, but maybe there is. It's something that I have not studied to the depth to see if it will give us more, if it will be less localized.
Okay, then one by myself. Core capabilities of a lifelong learning system. 5, safety and monitoring, ensuring correct behavior in a system that continues to change. What do correct and ensuring mean here, assuming that it's impossible to a priori predict all possible system environment states?
So that's very good. So we cannot see all the possible environment, and to say what is right and wrong is a very hard thing. So in general, I think you can have, well, everything that I will say now, I will kind of be sorry later. So there are things I think about when you drive, you sometimes feel that you need to stop in the middle of the intersection and turn off your engine. It's possible that there is something that will cause you to do that, but you'll have to have very good reason. So I think about the same about lifelong learning. Usually they have to follow normal regulations. And once, like, you may stop very fast in order not to kill somebody. You may stop there because people coming from all directions, and that's the only safe spot. So if they come to a solution, they have to have a good reason for that. And in addition to that, you can define all kind of safety issues beyond that.
Jan Musil. There. This is oddly specific. Could you please show again the slide with the UC Irvine group that is inspired by the hippocampus and the one after? Full stop.
Yes. So this is the UC Irvine, and the head of this group is Bruce McNaughton. Bruce McNaughton invented the hypothesis of the index code, and in the last 3 years managed to actually prove that that's how the cortex work, most likely. What this gives you is it explains to you why when you have to change something, you touch only very small and accurate piece of cortex rather than everywhere. And it gives you a very particular way of how you can avoid catastrophic forgetting. So this is their notion for that. This group is looking at somatic computation, and somatic computation is a very old way before animals had brain, where cells were communicating between them through electrical signaling. It's still not fully understood how, without the brain and how just locally, they would know what's the structure of the whole animal. As I mentioned, like with the planara, you can teach slow animals to do something, you can cut their head off and they still remember how to do that. So there is some memory in cells that we don't fully understand, and they have to go and understand it and tell it to us. Because if they tell us, we can build agent-based systems that will do AI by way of having some kind of localized memory and localized signaling.
Okay, so we're running out of time, but if you want to have more Hava in your life, which I think all of you should always want, she'll be back tomorrow, and she'll be back in 15 minutes, namely over at the AI Race and Societal Impact session at the National Technical Library. So out this building, turn right, next building. Everyone who signed up for it, go there, have fun, enjoy, and thank you, Hava.